Here we go. I will, let's see here. We'll begin with a word of prayer. Heavenly Father, we thank you again for your many blessings. Just ask that you guide our steps today. Help us to just understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. So today, I need to talk more about the magnetic field. To start with, I probably should just talk a little bit more about the force on a current. So, let's see here. So we can talk about the force on current distribution given, a magnetic field. All right, so the starting thing is you can just think about a line current, right? In this case, the current is simply equal to the charge density, linear charge density, times the velocity of the charge, right? So we can imagine, charges free to move along the wire, let's say, and they move, and that's the situation here, right? You got, the current moves like this, right? And so Griffith talks a little bit about, in principle, you could have multiple different charge densities, and like you could have positive charges moving this way, and you could have negative charges moving that way, and like they're together, they would give you a positive current this way. You could even think about like multiple species of charge, all moving different ways. But anyway, basically, we always just think of this. So that's pretty much what happens. But you could think about a more interesting composite current, I suppose. Like a real world example of that would just be if you think about a bundle of tiny wires, right? You could all put them all within some, big wire, like bind them together, and the total current going through that bound wire would just be like all of the little currents that are going, and they don't have to be all going the same way, right? Some would go this way, some go that way, and all together you'd have the net current. Anyway, in this case, you remember we had the Lorentz force law. So if I think about, like, this is dl, and then my little df was what? It was dq, right? Because there's just a tiny wee bitty charge here, right? And so that times the velocity of the charge, Cartesian cross product rather, with the magnetic field, which is given. All right. Then, of course, you could trade that for dq times dl dt cross b, right? Or you could do a dq dt times dl cross b, right? Or you could do a dq dt times the unit tangent vector times dl cross b. Or you could even do a dl times dq dt times the unit tangent vector cross b. Of course, this last thing I wrote, you might recognize as the current vector cross b. All right. So here's a bunch of different ways to look at the infinitesimal force from just a little dq moving with velocity v with respect to a magnetic field. And however you slice it, you have basically you got different options here, right? The magnetic force on the wire, you can either integrate, V cross B dq, but you could also do what? You could integrate I cross B times dl, right? You could also integrate I dl cross B. These are different options you have, flavor choices for how you want to calculate the net magnetic force on a wire, excuse me, with current I, all right? But then, perhaps more interestingly, we can also talk about like a surface current, all right? And here you've got like some ribbon, and so this distance, the dl perpendicular, all right? And we can talk about the surface current density, big K vector, which is equal to di vector dl perp, all right? And in this context, the magnetic force on a surface, a ribbon current like this, what you would do is you would integrate like, well, there's different ways you could look at it. You could do V cross B so let's see here. I'm trying to think about the charge that's on this little strip, right? So that would be what, like sigma times dA, right? That would be the dq that's there. So you put a sigma and a dA over here. That gives you the dq. It's the same principle that, you know, set up the other. But we could also write that in terms of the integral of the surface current density, right? We could set up this also alternatively as the integral of, I think just what this is, you know, the magnitude of K is what? It should just be like sigma V, right? In fact, I think we could just say this, right? So yeah. Anyway, so this can also be written as the integral of just K cross B, all right? And we integrate that over the area, that gives us the force. Then, of course, the most exciting, and these cases all matter physically. I mean, sometimes you get one, sometimes you get the other, but in here, we could think about, this was a surface current, right? This one, of course, the original one was just a linear current, but oftentimes we have a volume current, right? And so for the volume current, you want to think about kind of like a tube, right? Like that. All right. And so there you've got like dA perp, I think. And of course your current's going with velocity v, right? And the current density in this case is di dA perp. All right, so then, and so this, you could also write this as the current density times the velocity, right? Where here I'm talking about the charge density of the moving charges, all right? The free charges which are moving in the current. That's the rho I'm speaking of here. And in this context, the magnetic force we would calculate as, well, the integral of V cross B. Now my little dq is rho d tau, right? But I can trade that, of course, for the integral of J cross B d tau. All right. We may never actually even use these formulas, truth be told, but I think they're instructive for getting some idea about the distinction between a linear current, a surface current, and a volume current, right? Last time we proved Ampere's law, right? And what did Ampere's law say? We showed that the curl of B in the magnetostatic situation, whatever that means, I'll tell you more about that in a second. All right, we will circle back to that. But in the proper context, right, del cross, the curl of B is mu naught J. And then, of course, I told you if we integrate that over some surface, right, well, that's mu naught times the integral of J dot dA. Now, what is J dot dA? Well, what that's calculating over a given surface, right? So on the left-hand side, we used Stokes' theorem, right? And Stokes' theorem says that this is the integral around the positively oriented boundary of the surface. The circulation of the magnetic field, right, is equal to mu naught I enclosed. And so that, of course, is our familiar form of Ampere's law from like physics, from the introductory physics class, right? And well, we have derived that from the Biot-Savart law, right? Last time. But my larger point to you is that this current enclosed, if we're talking about a volume current, right? So it's, you know, there's some surface, right? And there's some kind of currents going through that, you know, going through that surface, right? And if we say that I mean, it depends on which. So you guys tell me, which side do you want to put the normal on? Like this side or that side? We can go either way.
The side going with.
So, okay, so like. So if I do that, then that makes, I think, these pictures are perilous, but so like, I'm going like this in my right hand, my positively oriented, right? So yeah, so in this case, the magnetic field which would be created by such current density, right, would be encircling that current in the way that, you know, goes into the board, behind the board, and around the board like that. But what I wanted to say is, to calculate the current enclosed, I mean, there's different things we do for different problems, right? In principle, current enclosed could be what? Like in this kind of situation, I mean, this current enclosed, I don't have a good place to write, but current enclosed could be the integral of, you know, K, well, let me stop that. I don't have a good example, so let me not spin my wheels in that direction. I'm just trying to say that to actually calculate the current which cuts through a surface, you might have to like think about either a linear current, right, or even a surface current or a volume current. And yeah. We'll actually see that in the example I have later, so let me just let that be answered there. So you guys asked the question last time, what do I mean by steady current, right? So that probably warrants, that should have been the first discussion we had in here, right? So my apologies, that's obviously, this is like, you know, out of order for sure. You deserve this discussion like 60 minutes ago. I don't know. So I picked up the wrong paper. So let's talk about the context for the Biot-Savart law. And more generally, magnetostatics. What do we mean by magnetostatics? This means that the magnetic fields are not time dependent, right? It doesn't mean that they're constant in the sense of, I mean, they're not spatially constant, right? Like I was just describing a magnetic field which wrapped around the currents, right? So they definitely have different directions at different space. They're not constant in that sense, but they are time independent in the magnetostatic context. And so here's essentially Griffith's definition. A steady current is one for which charge is not accumulating at any point. So mathematically, we can say we want the divergence of J to be equals to 0, and we also need that J itself doesn't have a time dependence. So these are the conditions we want for steady current. These are the fundamental assumptions of the magnetostatic discussion, is that we're looking at problems which satisfy these rules. All right? And if you look back at the derivation we did last time, we needed the divergence of J to be 0. And one crucial point, if we didn't have that, we wouldn't have gotten Ampere's law. There would have been a boundary term that would have spoiled things. All right. So, but of course that all then kind of begs the question, wait a minute, how true is the Biot-Savart law outside this context, right? And I don't have a good answer for that yet. We'll have to wait until I digest later chapters and think harder about my life. But there's a more basic question here that is underlying even before magnetostatics. Like, so electrostatics that we worked on before, of course, is the case that the electric field has no time dependence, right? It does have a spatial dependence, as we've seen. It points in all kinds of different directions, different space, different points, right? But those are static configurations, yeah? But what else is going on? I mean, there's something else to think about, which is what's the connection between current density and charge density, right? So if you think about some volume, V, right? And we wanted to talk about the total Q in here. What would be the total Q in that volume? We'd do what? We'd integrate over the volume the charge density times d tau, right? Now, so, all right. Now, if that charge is changing, what has to happen to the charge inside this volume? If QT is changing, what has to happen? I mean, charge has to leave the volume, or it has to enter the volume. Like, for the sake of discussion, let's suppose that the charge is decreasing in the volume. That means what? There has to be charge flowing out. What principle am I using there? What basic law of physics am I assuming in saying that? Conservation of charge, right? Conservation of charge says that if you look at some specific locale, if, the charge is, so this would be for dq dt, decreasing, right? There has to be an outward flowing current density, right? And so we could be more precise here, right? It has to be that dq dt, the total charge, and I'm going to drop the t here, has to be what? It has to be minus the integral of j dot dA, right? Because if this is decreasing and the current flowing out is positive, we need a minus here to be consistent, right? In other words, you could say this plus that has to be 0, right? Whatever you lose in the charge, you have to gain in the current flowing out, and vice versa. But you see, we can trade this for ddt of the integral over the volume of the charge density times d tau equals to, well, minus the integral over the boundary of the volume, you see, of j dot dA, to be more specific, right? But by now you're numb to it. We can bring the derivative inside the integral, right? I mean, what else would we do, right? That's all we ever do in terms of differentiating integral. We bring the derivative inside. Now, once we bring the derivative inside, right, so this is a number that's the total charge. So it makes sense that this is a total derivative, but once we bring it inside, it has to be a partial derivative because we're differentiating a function of several variables, you see. So partial rho, partial t, d tau. And on this side, how can we convert that to a volume integral? How about this? That's minus the integral over the volume of what? The divergence of j, yes, by the divergence theorem. Woohoo! But the volume over which we're doing this is completely arbitrary, right? This has to hold for any possible volume because charge is conserved at any scale. Therefore, we have that partial rho, partial t is equal to minus the divergence of the charge density, or if you like, the divergence of the charge density is minus the rate of change of the divergence of the current density is equal to the minus the time rate of change of the charge density. This is the so-called continuity equation. All right. And I thought you guys should see me work that out. So there it is.
So does that assume that J is continuous?
That assumes that J and rho are not independent. They are fundamentally linked. You cannot change J without changing rho. You cannot change rho without changing J. They're stuck together because they're just, this is, I mean, truth be told, this defines conservation of charge. I mean, I introduced it as a heuristic principle, but truth of the matter is, if you were to ask me to define conservation of charge, I would write this. To me, this is the definition of conservation of charge. But, all right. And what follows? There's many gory calculations, which I'd like to show you. Many of these things you have seen in the previous course. So, yes. I guess well, okay, yeah, I'll hold off. I thought I was further into the lecture than I was. Let me not do this yet. I will get to this, but let us first. Let me suffer through at least one writing it out. Yeah. Sorry, I'm trying not to be too lazy. All right. So we have the Biot-Savart law Now we actually want to work out some magnetic fields for some given current distribution. So I'll start out, this is my example 2. We'll get to example 1 at the end of class, if that's okay with you guys. Example 1 is a doozy. So example 2, we have steady current going in circular loop, radius r. And we're asked to find the magnetic field at a point distance z above the center of the loop. All right. So here's the deal. Trying to find the magnetic field up there. I'll picture a dl down here. All right. I guess I probably should remind you that the fundamental tool we have to work with here is the Biot-Savart law, which says that the magnetic field at r due to a current I is given by mu naught I over 4 pi z integral of dl prime cross script r hat over script r squared. Now, truth be told, guys, let me just erase this because I never ever use this. Every single time I ever do a calculation, I do the following. Third power and script r vector, because I'm just telling you in terms of like what's convenient for how I usually set things up, like that's what I do anyway. All right. So here's my current loop. So I've got my steady current going round and round, round and round she goes. Its distance z this away. This here is radius r. Yeah. And so, well, I decided to use cylindrical coordinates here because I can. Now, Griffiths is smarter. He does just some geometric thing. And we'll let him have his way in the example after this. But for now, I'm going to try to showcase some of the things we have to work with in terms of like the cylindrical coordinate frame. So this is script r, right? It points from the source point, source current segment, right? Up here, we're trying to find this is the field point. We're trying to find the magnetic field here. All right. So, can you guys tell me what is? So I'm going to put this point on the z-axis. I'm going to put the origin right here. All right. So I'll start you out. dl vector is straight up r d theta hat. Oh man. Oh man. I warned you this would happen.
Why is dl prime?
Phi hat. It's prime because it's the source current, but I'm not going to put primes on everything else because I don't care. Sorry. If every once in a while I feel guilty about it and I use a different notation for the field point, like r sub naught or something, and then I can use r without the naught for the source point and do my integral without knots or primes or whatever. This is a persistent notational nuisance in this course. Anyway, did you guys agree? Like the phi angle in the cylindrical coordinate system wraps around the z-axis, yeah? So that's the direction of dl. It's in the phi hat direction, and the dl is r d phi, r d phi. Okay? That one I can write as Well, I'll do the easy part. ZZ hat, yeah? So I'm going from here to there. So I did this part. What else?
Minus R row hat.
No rows. Row.
Wait.
We're in cylindrical coordinates. So we're talking,
S hat.
yeah, we're talking this is phi, and this is S, this is Z, you know? Yeah. So I heard a S, minus R S hat is what I was looking for, yes. So that's how to build the, you know, separation vector from the source current segment to the field point. It's just ZZ hat minus RS hat. All right. So then, if I calculate dl prime cross script r vector, I have r d phi hat crossed with ZZ hat minus RS hat. Now I will remind you the way this works. There is a circle of remembrance, S hat, phi hat, Z hat. That's the order of the coordinates, like so. And from this I remember that phi hat cross Z hat is S hat. So I get myself a RZ d phi S hat from the phi cross Z hat. And then phi hat cross S hat, that's going opposite the circle, so I actually get plus R squared d phi Z hat, yeah? Minus a minus give me plus there. All right. Now, by the way, what's R cubed here? What's R squared, rather? Fine, I'll write R. I can afford a square root. I can afford a square root. So it's just Z squared plus R squared, yeah?
Yeah.
All right. That's what makes this a super nice, like, physics 232 problem, actually, right? All right, so then my B of R is a mu naught I over 4 pi. Notice that the R cubed has no phi dependence, right? So we can pull it outside the integral. So we've got, like, you know, 1 over Z squared plus R squared to the 3/2. And then we're integrating. Our integration's over d phi, right? So 0 to 2 pi of RZ S hat plus R squared Z hat. Factored out my d phi. Does that seem fair? If it doesn't seem fair, I can bring this back inside the integral, so it's just manifestly what we're doing. What do we mean by that integral? We mean integrate over a parameterization of the object that describes the source current, right? And I've done that. What happens if we integrate S hat all the way around the circle, though? It integrates to 0, right? Now, if you want me to, so like exactly this piece, this integrates to 0, and we're just left with B of R is, you know, mu naught I R squared times 2 pi Z hat divided by 4 pi Z squared plus R squared to the 3/2, which we could clean up a bit. We have the magnetic field And it's not at any, I say at R, that's totally bogus. This is the magnetic field where? It's the magnetic field specifically at 0, 0, Z, right? That's the, this is false advertising right here. All right, I'll erase that. So there, anyway, so B, booze, is mu naught I R squared divided by 2 Z squared plus R squared to the 3/2. And of course it's in the upward direction, right? Now you're wondering, how did I know this integrated to 0? It's because S hat, remember, is nothing more than minus, no, it's literally cosine phi, sine phi, 0. So if you integrate over 2 pi, that integrates to 0, because sine and cosine both integrate to 0 if we range over 2 pi, and there's nothing else there except for those sines and cosines with respect to the phi integral. So of course, but I think it's also geometrically clear that if you integrate the S unit vector, right, all the way around the circle, you add those up, of course it adds to 0 because you're going, you know, equally symmetrically in all directions. So anyway, there you go. All right, I wanted to work that one out for you guys by hand. So there it is. That is not what Griffiths does. What does Griffiths do there? Well, I mean, he just appeals to some simple trigonometry, right? And draws a picture and just does that, which is what I would usually do in like Physics 232. But I think it's healthy to see how how our current, you know, newfangled calculus actually allows us to work these problems. You notice what I didn't do here? What did I not do here? I didn't do any kind of geometric reasoning whatsoever. Well, almost none. You know what I'm saying? Like, the geometric reasoning I did was to formulate DL in terms of like the phi hat, right? Or to build the R hat. But I didn't at any point have to do the right-hand rule to figure out which way the dB was pointing and stuff. Like, I don't know. It's say like, what was that? Anyway, I'm not trying to sell you on that's what you can always do. It's just smarter sometimes to use the right-hand rule to figure out which way the dB points, right? So, come on. All right. So, what was that example 1 I was talking about? Let's look at that for a second here. So example 1 was an honest-to-goodness, come on, this is at the start of Griffiths' magnetos. I think I got it plugged in. What's going on here? Am I on the wrong source or something? Does it say HDMI?
You're on 1, yeah.
Oh, okay. I didn't really do anything. That's not comforting. Because if I didn't do anything, if it starts not working again, there's nothing I can do to not, you know.
As long as you do nothing, it should do it.
Okay, yeah. Okay, so, all right. What you're looking at here, here's the problem. We have an electric field which goes in the z hat direction, a magnetic field which goes in the x hat direction. Our charged particle starts at the origin motionless. What happens? That's the problem. And so we can actually work out the math here with relatively little differential equations, believe it or not. So like I work out the Lorentz force, it ends up being just in, it's got the electric components in the z direction, but the magnetic component is in the y and the z direction. So there's some kind of intertwangling between the electric and the magnetic forces in the z direction. But anyway, so when I look at F equals to ma, see this is A, x double dot x hat, y double dot y hat, z double dot z hat, right? This is A, yeah? I have this lovely system of coupled second-order differential equations to solve. But the cool thing is here, you can actually solve them. We can actually do it. It's not that bad. First of all, this equation is precious because, like, once you introduce the cyclotron frequency, which is QB over M, just reduces the clutter in this problem immensely. Well, look at that. If you've got a derivative everywhere, just integrate that thing, right? Integrating that gives me y dot is omega z plus a constant, right? And once I see that, well, then I can plug it into the other one. You know, I integrate this one, plug it into the other one, see, because it's got the y dot here. So I replace that y dot with this business. Cool stuff happens. When I rewrite this, I get z double dot plus omega squared z. Oh, constant coefficient in z, yay. And this is just a constant. So I can solve that pretty easily. The solution is just this. My particular solution is just particularly this. And, or you could call this this is the homo solution. And this over here is the no homo solution. You could say that as well if you wanted to. If you wanted to use that kind of language, you could. But anyway, so then, of course, y dot is then obtained because it's this, right? So there's my y dot. There's something cool that happens when you plug in this. There's like the C1 term cancels. It's really cool. Anyway, so that happens. And then integrate, you get there. And then I just apply the initial conditions, which isn't especially interesting, but after a bit of algebra, it's really not bad, truthfully. You find your way to this particular set of solutions. Y is equal to that, z is equal to that, which I don't know, they're gone now. Sorry, you guys know I'm easily distracted. This doesn't mean anything to me particularly, but if you eliminate the sine and cosine by using sine squared plus cosine squared, something really cool happens. You get this boxed blue equation, namely that y minus r omega t squared plus z minus r squared is equal to r squared. Well, this is the equation of a circle, but it's an equation of a circle with a moving center. The center is at r omega t for y and r for z, and you see, so like as the time progresses, you know, the circle, and so you get this, which is of course a cycloid. It's very cool. I'm very excited that you can actually solve this problem. You know, like you can straight up find the solution. It's precious that we can do this. It's cool. What would happen if you added a little like x velocity at the start? Ew, it would be so much. I mean, it would just make it drift in the x, you know. But ooh, I don't know. I don't know how much worse it would be if it started with a little bit of x. Okay, so we talked about this, talked about that, and we did this example, right? The next example is the standard one that you guys all saw in like 232. You have a line current, right? How do you find the magnetic field due to like a long line current at a point, you know, S from the current? So I'm like, well, I'm going to put the current in the x direction. I'm going to let it go from x1 to x2, and I'm going to use my, you know, formalism to build the cross product of dl cross r. So I did that, like so, and I worked it out. And it works. It works, right? There's the usual trig substitution there, and you get the difference of the signs. And then, of course, if you think about it, if you let you know, x1 go to minus infinity and x2 go to infinity, you end up with this going to like 1 minus a minus 1, which gives you a 2, which then gives you this, you know, mu naught I over 2 pi s in the phi hat direction. And if you want to rewrite the the line like this, the current like this, then the magnetic field circling the current like that, okay? So this is standard stuff, but I mean, it's okay. But Griffith's way of setting it up is actually really important to know about because it gives you a formula which is useful for a wide variety of like slightly twisted problems. It's important to know about this. So his setup is to go with a little finite line segment of current. Now, this obviously begs the question, how can you have current that just goes from here to here? Like, what's that? How is that steady? Okay, so the idea is that we're just thinking about a particular segment, right? It's not the whole story. The whole story is that there's a bunch of segments and they're all linked together and they collectively make a closed circuit, you know? So this is just part of the story, but superposition says if you can do one segment, you do another, you add them together because we have the superposition principle from the Biot-Savart law, like just the mathematics is right there. Because the integral is linear, so we have superposition. But anyway, so this one, he sets it up like this. Now there's some super sneaky steps in here. Look at this. So like, first of all, the magnitude of dl cross r hat. All right, great. So he draws this picture, fair enough. Here's my dl, here's my point, distance s from the line, right? Fine, nothing hinky there. Alpha is the angle between dl and r. D. The thing. Right? So the data is like, yeah, it's the angle here is theta, right? anyway,